Hello everybody, I hope all of you are doing well. Today we're going to be solving a problem on centroids and moment of inertia of composite. Okay, so let me first write down the problem. So for the given composite shape, and I'll go over the composite shape in a minute. For the given composite shape, let us locate the centroidal axis and then obtain the moment of inertia about the centroidal axis. Okay, so for a given composite shape, obtain the centroidal axis and also obtain the moment of inertia about the centroidal axis. Okay, and this is a standard problem that you will encounter when you're looking at things in strength of materials and so on. Okay, alright, so two things that I'm going to underline. First is the centroidal axis, and then moment of inertia about the centroidal axis. And what kind of a shape is this? This is a composite shape. A composite shape is nothing but a combination of simple connected shapes. Okay, and simple connected shapes in that sense are rectangles, circles, or triangles, and we are exclusively concentrating on rectangles alone. Okay, so here is a shape that is given to me. Alright, so in this shape I have a long thin web here, which is of a thickness of 80 millimeters, and then I'm going to have all these distances that are marked in the figure. Okay, 380 millimeters is the total width of the top flange, and then there is a small cutout of 60 millimeters, and then looking at the heights, I have 40 millimeters starting from the top all the way to where this arrow ends here. Then I have 80 millimeters and 210 millimeters. So typically my plan of attack is to always start off by setting up a coordinate frame. Okay, so my plan of attack, let me write down my plan of attack or solution. Okay, so set up a suitable coordinate frame and choose an origin. Coordinate frame and choose the origin carefully. Okay, then obtain the centroid. Okay, the formula for the centroid is the area weighted average of the centroid of the individual shapes. Okay, by using the area weighted average of the centroid of the individual shapes. Individual simple connected shapes. Okay, then we come to the moment of inertia calculation. Once the centroid is obtained, then mark the centroid of each of the pieces. And I guess in a sense I should mention that once I set up the suitable coordinate frame, I divide it into simple connected pieces. Okay, so choose the simple connected pieces. Right, once again, we have seen in previous problems that there are several ways one can do this. Okay, then mark centroid of each of the pieces, the simple connected pieces, and then we make use of the fact that okay, then you mark the distances between the main centroidal axis and the centroid of each of the pieces, and you'll see those steps being carried out. Okay, and once you do that, then you just say that the moment of inertia of the entire composite shape, moment of inertia of the composite shape will be given by the application of the parallel axis theorem. Okay. Via use of the parallel axis theorem. Okay. So a couple of keywords here: simple connected pieces. That's the first thing. Suitable coordinate frame with an origin chosen. Then using the area weighted average. That's another word that you want to note here. Then mark the centroid of each piece. Once you do that, the moment of inertia calculation can be done. Okay, and this will be done by using the parallel axis theorem. And you'll see how this application is being done. Okay, all right. So let's get down to business. Let me take the composite shape, and then let's start using the idea of the centroids. Okay, so I'm going to take all of these guys, then copy that, and let's do this problem very carefully. Okay, so first is centroid calculation. These are fairly straightforward problems. The only issue here is that if you make a mistake, then everything goes bad. Okay, if you make a mistake on calculating the centroids, then everything goes bad with respect to the moment of inertia. Okay, so here is the situation. Let me bring it down onto the side here. All right, this is fantastic. Now here is what I'm going to do. I'm going to break it up into simple connected shapes, and I immediately recognize, okay, here is one simple connected shape that I can draw. Of course, it has to be a straight line, and you know my struggles with a straight line this semester, or probably for the rest of my life. Okay, so here is one simple connected shape that I can draw. Okay, then I'm going to draw the next one, which is this guy here. Okay, I'm going to break that down. Of course, I'm going to have that and all of that, and this piece here. Okay, then comes my third simple connected shape, which I can say, okay, he's going to go from here, okay, all the way down to here. Okay, that's beautiful. So three simple connected shapes. So let me call that as shape 1, 2, and 3. So here is shape 1. Then this is shape 2. And this is shape 3. Okay. Then what do? I have to set up a coordinate frame. Okay, so to set up the coordinate frame, I choose a suitable origin such that I have everything positive. Okay, so here is my coordinate frame. I'm going to set up a coordinate frame such that this is going to be my y-axis, as you're going to see it here. Okay, and this is going to be my x-axis. And this is going to be my y-axis. The reason for doing that is so that all the distances that I'm going to mark now are going to end up being positive. Okay, and here is the origin O. Okay, once I do that, then I mark the centroid of each of these little pieces. Okay, so here is the centroid of the first piece. Okay, or the third piece, I guess. Then let's see, here is going to be the centroid of this second middle fellow there, and then probably where I have marked this 80 millimeters should be close enough to the centroid of this third piece. Let's say that it's somewhere here. Okay, and let me move my 80 millimeter thickness a little up there. Okay, so these are the distances that I have marked on the figure which were given to me. So this is C1. Okay, then this is going to be C2. And this is going to be C3. Okay, these are the centroids. Then from the origin chosen, I'm going to mark the distances of each of these. Okay, look at this. So this height here is going to be y1 bar. Okay, so I'm going to start off with that. So start from the origin. So these are one directional arrows. So this is going to be y1 bar. Okay, then I'm going to have all the way on to here. Of course, hopefully straight line. And let me maybe extend this so that I have all of these coming in. Then all the way from there to there I have y2 bar. Okay, then all the way from the origin to C3 I have y3 bar. Okay, and let me make sure that these are dotted lines and so on, so that they don't mess up with our idea of what this is. Okay, and one directional arrow, so that you see that, okay, where is the positive origin, or where is the origin. Okay, so these are my distances, y1 bar, y2 bar, and y3 bar. It's very obvious to see that y1 bar is going to be half of 210, y2 bar is going to be 210 plus half of 80, and y3 bar is going to be 200 plus 80 plus half of 40. Okay, and likewise I'm going to mark x1 bar, x2 bar, and so on. Okay, so starting from here, I guess I'm going to have 3 lines. So first line, which I'm going to bring on here. Okay, then I'm going to bring a second line from here, a little deeper, and then the third line. So this is going to be a little tricky, right? So the third line is going to come down here. Okay, so what are my distances? So this is going to be x1 bar. Okay, then I'm going to have x2 bar. Watch this. x2 bar is all the way from here to here. So in the meantime, let me put this here. So x2 bar is going to be all the way from here to there. Okay, so that's going to be x2 bar. And then I'm going to have x3 bar this way. So let me do the following. Let me bring this down a little more. That was not intended, but that's starting there, and let me pull this down here and pull that down there, and then so this is going to be x3 bar here for me. Okay, so that I have all of them written without getting jumbled up. So look at x3 bar, it's starting from the origin all the way to where the centroid of the third piece is. Okay, so now I have to draw these as dotted lines, and then we should be on our way. We're pretty much done. I mean, once you have these things marked out, all you need to do is just be careful. That's all. Okay, and there are many ways of breaking this piece into simple connected pieces. I've just chosen one particular way. One good idea is maybe try a different way of breaking it into simple connected pieces, and then calculate the moment of inertia. Once you do that, you got to see what the answer is going to be. Might be a useful exercise. Okay, so in this case I have x1 bar, x2 bar, x3 bar. x1 bar is easy, it's half of 80. x3 bar is going to be, if you look at this here, so that's 380 and then 60. So here is what I can do. Look at this. So I'm going to take this 380 and then bring it up a little bit. Okay, so that becomes the extent of all of that. And then I'm going to take this guy and then bring it here and stop it there. Okay, and of course that's not 60. I can get rid of that. That's going to be 380 minus 60, so that's 320 millimeters. Okay, so here is the thing for that. Okay, and so that is going to be 320 millimeters, because the remainder of the piece was 60 millimeters. So I have all the distances and so on as well. Okay, for each of these little pieces. Okay, that is very good. So we're done with that, and let's see. Anything else that we need to do here? I guess that's about the only thing that we need to do in these things. Okay, and maybe if you want, you can mark these as dotted lines as well, just because they're also things that denote dimensionality and so on. Okay, just to make it look a little cleaner, I'll go with the same logic for all of these pieces. More than solving the problem, it's these things that take up time. All right. So I have everything set up. Then the question is just writing down the values of each of these. Okay, so if you look at this, let me start off with x1 bar. X1 bar is going to be half of 80, and then y1 bar is going to be half of 210. Okay, so let's start off with the first piece. Okay, so piece number 1. X1 bar is going to be half of 80, so that's going to be 80 by 2, so 40 Then y1 bar, if you look at this is going to be half of 210. Okay, that's 210 by 2, so that's 105 millimeters. And then the area A1. Okay, so what is A1 going to be? A1 is going to be the thickness, and I guess we had to have this in the same color, so let me put it in the same color here. Okay, so that distinguishes the third piece. Okay, so these are our 3 pieces, right? And I guess I need to do one more thing here. I forgot to, well, I did not forget. I think it's the y-axis that caused that issue where all those lines became black lines. Okay, so area is going to be 80 times 210. Okay, so that's going to be 80 by 210 and here is further what I'm going to do, the base and the height. Okay, because I'm going to do moment of inertia, I need to write down the base as well. So the base is going to be 80 and the height is going to be 210. Okay, so the base B1 is 80 and then the height H1 is 210 and then I'm going to do the same thing for each of the other pieces as well. Okay, so I'm going to do piece 2. Okay, and let's say that I make up a little more room for that. So this is all the stuff for the first one. Now I'm going to do the second one. So I'm going to write x2 bar. X2 bar, as you can see, is going to be half of 380 millimeters. Okay, so that's for the second piece. So 380 divided by 2 is 190 Then y2 bar is going to be, if I go here, it's going to be 210 plus half of 80. Okay, so this is 210 plus 80 divided by 2, so 250 millimeters. Okay, then A2 is going to be the following, right? A2 is going to be 80 times 380. Okay, so 80 times 380. Okay, then I'm going to have B2 and then H2. Be careful here, the base is always the one that is parallel to the x-axis. In this particular case, that's going to be 380. The height is going to be 80. Okay, so this is going to be 380 and the height is going to be 80 millimeters. And then we come to the third piece. Let me bring all of these a little down from where I had marked the x2 axis so that we see what we're doing here. Okay, so we come to the third piece now and we follow the same procedure. Okay, start off with x3 bar. And for x3 bar, I'm going to have it as a half of 320. Okay, so this is going to be 320 divided by 2. Okay, so that's going to be 160 millimeters. Then y3 bar is going to be the following. Okay, it's going to be 210 plus 80 plus 40 by 2. Okay, so 210 plus 80 plus 40 by 2, and if you do all of that, that's going to be 310 millimeters. And A3, if you look at that, that's 40 times 320. Okay, and then B3 and then H3. Okay, B3 is the base, which is 320 and the height is 40. Okay, so this is 320 40 and that's about it. Then all I have to do is apply the formula. Okay, the formula for centroid of a composite shape. This is something that you have seen in the past. Okay, so here I have x bar is the centroid of the composite shape from the origin that I have chosen. This is going to be summation I is equal to 1 to n xi bar ai, all of this divided by summation I going from 1 to n, where n is the number of simple connected shapes, and then I'm going to have y bar is likewise summation I is equal to 1 to n yi bar ai, and all of this divided by summation I going from 1 to n ai. Okay, so this is the basic formula. So we have three shapes, so our aim is to go from I is equal to 1 to 3. Okay, so if I write the formula for us, so for us I is equal to 1, 2 and 3. Connected shapes. Okay, so now I'm ready to write the formula, and then I'm just going to plug in the numbers and so on. I'm not going to actually do that. You can do that and check the answers and so on. Okay, so I'm going to get x bar is equal to x1 bar a1, x2 bar a2, x3 bar a3, all of this divided by a1 plus a2 plus a3. Okay, and we have all these values as seen here, x1 bar, x2 bar and x3 bar, and then a1 and a2 and a3. So substitute and then solve. This ends up being around 141.6 millimeters. I usually use it up to 1 decimal place, and then y bar is going to be likewise y1 bar a1, y2 bar a2, y3 bar a3, all of this divided by a1 plus a2 plus a3. Okay, and if you do the substitutions, then you'll end up getting this to be 222.2 millimeters. Okay, so this is obtained by substituting from above. Okay, so obtained by substituting from above. Noted values. Okay, what are those values? Those values are written down here. Okay, so you do this for each of the pieces, then you're good to go. You can basically just keep plugging it into your calculator, just glorified plug and chug. Okay, so this is the formula for the centroid, and this is the location of the centroid. Okay, so which implies that now I know the location of the centroid. Here is what I'm going to do further. I'm going to take my thing from above, the one that I have drawn, and then start doing the moment of inertia calculation. Okay, so now let's see if I have enough space. I think I should have enough space here. So now moment of inertia. Okay, about the centroidal axis. Okay, so we're good to go almost. Okay, so here is the centroid calculation. Now I have to see if I can capture all of this in one fell swoop. So I'm just going to reduce the size here and go and get this creature out. Okay, all right, that should do it, I think. Come back here, put up all of these in a good way. Okay, so I have everything done here. Okay, now I know the locations of all of these and so on, and the geometric details are also known to me, so I'm going to get rid of some of these unnecessary values here. So all these geometric details are known to us, so I'm going to cull that out. Okay, and I'm going to get rid of all of these as well. One can get the values if needed. Okay, so x1 bar, x2 bar, x3 bar, these are all known to us. y1 bar, y2 bar, y3 bar, I can get rid of my good friend here. Okay, I don't need that for the time being. Now I locate the centroid of the main body. Okay, so we know the centroid of the main body, so we calculate it. that x bar is 141.6 millimeters, and then y bar is 222.2 millimeters from the chosen origin. Okay, so let me bring this down here. Okay, so maybe I can write that here. I guess I'll just leave it here. Okay, so this is from the chosen origin. Okay, so that's from the origin O that we have here. So from this particular origin, if I go a distance of 141.6 millimeters, I get the centroid of the main body now, and a distance of 222 millimeters. So obviously, where is the centroid going to be? 222 millimeters is a little larger than 210, which I had as the height of the piece here, right? So if you go back here, 210 is the height of the piece, so 222 is going to be a little more than that. And then the total width of the first piece was 320, so I'm going to have the 141 well inside. Okay, so let's say that, the centroid of the main piece is going to be somewhere here. Okay, so let's see. Okay, so this is going to be the centroid of the main piece. Okay, so let me call that as capital C. Yes, I'm running out of space to do that, but let's see. So this is capital C here. Okay, so that's the location of the centroid, and what I'm going to do is maybe clean up all of these as well, as you know. Okay, so I'm going to get rid of all of these things here as well. Cut that off, and I'm going to do a few things, as you are going to see. Okay, so now I have my nice and clean figure here. So the first thing I'm going to do is add the centroid of the main body. So this is from the origin O, and this is labeled as C here. Okay, so this is labeled as C. Well, trying to draw a straight line. Okay, very good. And I'm going to bring this down a little bit. Okay, so that I have enough space to mark all the things that I want to mark. Cut this off as well. Well, let me keep that for the time being. Okay, so I'm going to now mark all the centroidal axes. So I'm starting off with the first one. Okay, so here is going to be the first one, which I'm going to call as XC. Okay, this is the main centroidal axis, right? So you can call this as X bar C if you would like. Okay, and then I'm going to have Y bar C, which is starting all the way and then going up here. Okay, so let's mark this in a dark line. So this is going to be Y bar C. Okay, so X bar C and Y bar C is the main centroidal axis. Then I start off doing the same thing for the other ones as well. Okay, so let's do it for this one here. So this is going to be X bar C1. Okay, and then all the way from here to there is this guy. I'm going to try to make it as a straight line, then scoot it up here. So before I do that, let me do the following. This is C1. Very good. Beautiful. Okay, then this is going to be Y bar C1, as you can see. Then I'm going to have C2. Okay, so C2 will give me X bar C2. Okay, this is X bar C, which is the main centroidal axis. Okay, as you can see here. And then there's going to be one more here, so that's going to be Y bar C2. I'm just marking all these centroidal axes for the individual pieces. Okay, so this is Y bar C2, and then I'm going to have C3, which will help me mark this guy here, so which I'm going to call as X bar C3, and then I'm going to have Y bar C3. So it's getting a little crowded here. Okay, so this is Y bar C, the main centroidal axis, and then let's say, okay, that should be better. So that's going to be Y bar C3. So all of these have been marked, and Once you have done that, then all I have to do is start looking at the distances between the parallel axes. Okay, so let me first write down what these things are. Okay, so x bar c, y bar c is the main centroidal axis. Okay, and then x bar c1, y bar c1, x bar c2, y bar c2, x bar c3, y bar c3. Okay, these are the individual centroidal axes. Okay, and if you want, you can get rid of this as well. We don't need that anymore. We already know that the origin was the one that was located there, and from this origin is where the centroid location was also marked, and so on. Okay, so these are the things that I have so far. Okay, and that's a C2 there. Okay, once I have these, then I start marking the distance between these parallel axes. Okay, so here are the distances. First distance is going to be, so let me draw this line right here. Okay, so this is the first distance that I'm looking at. Okay, then the second distance I'm looking at, so this distance I'm going to call as the distance dy1. Okay, dy1 is a distance between xc1 and xc bar, these two axes. Okay, then I'm going to have dy2, which is the distance between x bar c and x bar c2. So if I scoot this down here, okay, then I can say, well, I'm just going to extend this line here in order to write my distances. Okay, and I'm going to extend that line here as well, and I guess I want to give me 1 second so that I can write this way. Okay, and I'll bring this down here. Okay, very good. And this distance here is going to be dy2, which is the distance between x bar c and x bar c2. Okay, so this distance is going to be dy2. And then lastly, I have the distance dy3, okay, which is the distance between x bar c and x bar c3. And that's going to be all of this guy here. That's going to be dy3. Okay, let's mark these in dotted lines. That's one there, then that's going to be one there, and of course that's going to be the third one. Okay, and let's put that as dotted as well. Okay, so that's the distance between these parallel axes. Then I have a whole host of such distances to be marked here as well on the top. Okay, so let me start off by saying, okay, hey, what is this distance here? This distance is the distance between yc bar and y bar c1, so that's going to be dx1. Okay, so that is the first distance. Then I have to have a distance between c3 and c, and then c2 and c. Okay, so first thing is, okay, start from here. Bring this down here and bring this down here. Okay, so this distance is going to be marked as dx2. Okay, and then let's put these as dotted lines with your silent permission. And I'm telling you, this is typically what takes a longer time, putting these as dotted lines and so on. Okay, and then I'm going to have the distance from C2 to C. Okay, and if I extend this line here, okay, that's going to be dx3 right there. Okay, we're almost done. And once you have these things, it's just a question of writing down the values of these distances, making use of what we already had from before, and writing the formula, and then moving on. Okay, all right, so a lot of hard work was done here. So dx1, dy1, dx2, dy2, dx3, dy3, all of these are distances, and let's write down what these distances are. Okay, so first of all, dx1, dy1, in brackets, dx2, dy2, dx3, dy3. These are distances between the main centroidal and individual axes. Okay, between the main centroidal axis and the individual axes. Okay, between the main centroidal axis. Okay, the main centroidal axis is x bar c, y bar c, and individual ones are all these small things that you've written down here. Okay, so let's start looking at what these are. So I'm going to just have it as 1. Okay, so in the first piece I'm going to have dx1 and then dy1. Okay, and here is what it is. What is dx1? dx1, if you look at that, is the distance between the centroid location C and the centroid location C1, right? So which means that that's going to be x bar minus x1 bar. Okay, so this is going to be x bar minus x1 bar. Okay, likewise, if I look at dy1, it's going to be the distance from the point O to the C1 location, which is going to be y1 bar, and then from point O to C, which is going to be y bar. Okay, so which means that this is going to be y bar minus y1 bar. Okay, and let me do the same thing for the second one, dx2 dy2. So once again, what are dx2 and dy2, dy1, dx1, and all these things are distances between the individual axes and the main centroidal axis. Okay, so if I look at dx2, what's that going to be? That's going to be the distance from the point C2 to the point C, right? So that's going to be, I guess I marked them as, sorry about that, this is supposed to be dx2 here, apologies. This is dx3, this is dx2, sorry. dx2 is the distance between C2 and C, so that's going to be x2 bar minus x bar, okay? So x2 bar minus x bar, okay, and then dy2, obviously is going to be y2 bar minus y bar. As you can see, going from point O to origin, and then point O to C2, okay, so that's going to be y2 bar minus y bar. And then the third one, dx3 and dy3. Okay, so dx3 is going to be between C3 and C, so that's going to be x3 bar minus xc, x bar, okay, and dy3 is obviously going to be all the way to the top right, so that's going to be y3 bar minus y bar. Okay, and if you want, you can bring the other things that you've written for parts 1, 2, and 3 as well. So let me do that. Okay, so here we had a whole host of information available, right, for these things. Copy that and let me bring it down here. Okay, so that goes with the first piece. Then let me do the same thing for the second piece. All of these things, copy that and then bring that down here. Okay, so that's for the second piece, and then the third piece likewise. Okay, so you see the usefulness of writing all of these things. All right, so these are the three things that I have, and let me scoot this onto the side a little bit more so that they don't look too cramped up. Okay, and if I want, maybe I just draw a straight line separating each of them, if I can draw a straight line. Alright, that seems better. Alright, so we're almost done. Once you have these things done, what do I have to do after that? Okay, well, I need to write the main formula. Okay, and of course in this we also have the other thing that I need to write down here is x bar and y bar, right? For each of these you have to subtract it from x bar and y bar, right? So we got to write down what x bar and y bar is. And also we know x bar is 141.6 millimeters and y bar is 222.2 millimeters from origin O. Okay, all right. So once I am doing this, then all I have to do is write down the following. Okay, so moment of inertia of a composite shape, the formula that we're going to use. Of composite shape about the main centroidal axis this is equal to the sum of the moment of inertia of the individual simple connected pieces about the main centroidal axis. Okay, this is supposed to be axis because I'm going to do it 2 times, right? Put the x-axis and the y-axis. Okay, so this is the basic rule or the basic formula. Okay, then let's start writing this down. So I x bar about the main centroidal axis C. This is going to be what? Individual pieces. So I x C bar for the first simple piece. Then this is going to be ix about ix z bar for the second simple piece, and then about ix c bar for the third simple piece. Okay, because there are 3 pieces. Okay, so 1, 2, and 3 refer to the simple connected pieces here. So 1, 2, and 3 refer to the simple connected pieces. Okay, and x bar is the main centroidal axis. But then we obviously realize that the main centroidal axis, if you look at this figure here, is not the same as the centroidal axis of the individual pieces. So I have to apply the parallel axis theorem. Okay, so since the main centroidal axis is not coincident with the centroidal axis of the individual pieces, of the simple connected pieces, we need to use the parallel axis theorem. Okay, this is the reason for using the parallel axis theorem. And then how do I employ that? Okay, so here is how I do it. So I x bar c is then going to be I x bar c1, okay, about its centroidal axis, plus a1 times the distance between the 2 parallel axis square, distance between x bar c1 and x bar c. Okay, likewise I'm going to have I x bar c2 plus a2 times the distance between the 2 parallel axes, x bar c and x bar c2. Okay, then likewise I'm going to have I x bar c3 plus the distance between the 2 parallel axes square multiplied by the area. Okay, and then all I have to do is just do the substitutions. Okay, so if I look at ix bar c1, so ix bar c is going to be ix bar c1 is going to be about its centroidal axis. I got to use the the moment of inertia of a rectangular piece. Okay, so that's something that you got to remember. Okay, and maybe I'll just write a brief note of it somewhere here. Maybe I can do that here. Okay, let's put a brief line here, and I guess this is information that we need, right? So always remember okay, for a rectangle base B and height h, okay, ix bar is 1/12 bh cube, and then iy bar is 1/12 hb cube. Okay, so please remember this particular formula. Okay, for a rectangle of base b, okay, and then height h. All right, so once I have that, then all I have to do is just start plugging it in. So this is going to be 1/12 b1 h1 cube plus a1 times dy1, which we had written as the following. If you look at dy1, that's y bar minus y1 bar, the whole square, plus 1/12 b2 h2 cube plus a2 times dy2 bar, which we had written as y2 bar minus y bar, the whole square, and then the last one. Okay, this is 1/12 b3 h3 cube plus a3 times y bar 3 minus y bar, the whole square. Okay, substitute for these values, which I'm not going to do. Okay, use the numbers given above. Okay, so using values for all the quantities as noted above, substitute, okay, into this one, and I will end up getting x bar c as the following value. So 4.33 times 10 to the power 8 mm to the power 4. Okay, so that's 10 to the power 8 there, and but then this is millimeters to the power 4, so I've kept everything in millimeters. You don't need to convert it into meters and so on. You can leave it in millimeters as well. Okay, so this is the first answer that I have. Then I go to iy bar, same idea. This is going to be iy bar of c of the first piece, iy bar c of the second piece, and then about this axis for the third piece as well. And obviously, since they're not coincident with the main centroidal axis, I have to use the parallel axis theorem. Okay, so which means that y bar c is going to be y1 bar plus a1 dx1 square. Then this is going to be y bar 2, okay, which we had written here, or I had yc1 and yc2, so sorry about that. This is going to be yc1 yc2 and then a2 times dx2 square, and then the last one y bar c3 plus a3 dx3 square. Okay, this is the distance between the two parallel axes. Okay, so if I'm looking at the y-axis, the distance is going to be along the x-axis. If I'm looking at the distance between two parallel x-axes, centroidal axes, the distance is going to be in the y direction. Okay, so if I do the substitutions, okay, so this tells me y bar c is 1/12 h1 b1 cube, a1 times dx1 is going to be x bar minus x1 bar whole square. Then, and make sure that is still the case, x bar minus x1 bar, and the rest of them are all x2 bar and x bar and x3 bar and x bar. Okay, so this is going to be 1/12 h2 b2 cube. Do not forget to write it as h2 b2 cube, because you're doing it about the y-axis now. Okay, the y-axis is vertical, the x-axis is horizontal, always, in this particular situation. Okay, so do not flip the two. Okay, and that's something maybe I should write down here as well. Okay, x-axis is horizontal, and the y-axis is vertical. Okay, that's something that you want to remember as well. Okay, and then do the filling of the details here. So this is a2 times dx2 is going to be x2 bar minus x bar square, and then the last one 1/12 h3 b3 cube, a3 times x bar 3 x bar whole square. Substitute, and then you'll end up with I y bar c as the following number. Okay, so this is going to be 7.3 times 10 to the power 8 millimeters to the power 4. Okay, and we had already obtained x bar c as well. Okay, so that's something that you want to remember. Okay, and when you're doing the x-axis and the y-axis, the moment of inertia for the rectangular shape flips from 112 bh cube to 112 hb cube. Okay, so that's the end of this problem, and let me very briefly walk you through the process once again. Okay, all right, so here is the problem. For the given centroidal composite shape, find the centroidal axis, moment of inertia, and so on. And many ways to divide this into pieces. I mean, I could have easily done the following, right? I could have just drawn a line here, and that's another way of breaking it up into smaller pieces. I could have done that as well. Okay, that's equally valid. You can do it that way too. So I have 3 simple pieces this way, but I did not choose to do it that way. I chose to do it in the following manner here. Okay, what are the steps? The steps are, first is I set up a suitable coordinate frame and then choose the simple connected pieces. In which way are you going to do it? Once you do that, obtain the centroid using the area weighted average of the centroid of the individual shapes. Then mark the centroid of each of the pieces, and then moment of inertia will be obtained by the parallel axis theorem. Okay, this is the solution. And here we set up by looking at each of the individual centroids, C1, C2 and C3, and then locate the origin. Okay, so the origin was chosen to be right down at this particular point here. Okay, that is the point O. Here is the origin for me. From this origin, I start marking all the distances, x1 bar, y1 bar, x2 bar, y2 bar, x3 bar, y3 bar, and so on. Okay, then I make a list of all of the details, as you can see here. Okay, so for each and every one of them, okay, so we write down what are all the things that are of interest to us. And let me do the same thing that I had done for the previous case. Okay, and then you make use of the formula. Okay, so here is the formula. This is the area weighted average formula, as you can see. Okay, and then it is just plugging and chugging. This is essentially glorified plugging and chugging, but it's very useful when you're doing stress analysis. You need to know these things for stress analysis. Okay, then I have the formula. Once I have the formula, we have 3 simple connected shapes in our problem. So if I do the formula, x1 bar a1, x2 bar a2, x3 bar a3 by a1 plus a2 plus a3, and likewise for y bar. Okay, obtain the values. Once you obtain the values, then you got a lot of busy work to do. Okay, the moment of inertia about the centroidal axis. Okay, one thing that you know is, okay, where is this obtained from? The value of these quantities is obtained from the origin that you have chosen. So that is very important to understand. Okay, this is not some arbitrary number. If you chose a different origin, you will get a different value for the centroid, but your moment of inertia should still end up being the same value. That is something that you want to note. Okay, so maybe a quick note here. If I chose a different origin, x bar and y bar will be different, but the moment of inertia, I x bar and I y bar, should be the same. As obtained in this problem. Okay, so one way is choose a different origin, see if you get the same answer. That's another way of just cross-checking yourself. Okay, then I mark the distance between all the parallel axes, x1 dy1 dy2 dy3 dx1 dx2 dx3. Okay, and once I do that, I make a list of all of these details, numbers, and so on. And then I remember a couple of things. For a rectangle of base b and height h, I x bar and I y bar are the following formulae, and x is horizontal and y is vertical. Okay, and if you do the other way, it flips around. Then the basic idea is moment of inertia of the composite shape is the sum of the moment of inertia of the individual simple connected shapes about the main centroidal axis. Okay, depends on which axis you're looking at. If you're choosing a different axis, then you got to do the same idea for a different set of axes. Okay, but the parallel axis theorem will still be useful because it is not necessary that the centroid of the simple shapes be coincident with the centroidal axis of the main shape. Then I make use of that fact here, and then I say, okay, since they are not coincident, I use the parallel axis theorem, plug in the numbers and get ix bar c. Likewise, the same story for iy bar c. Okay, so I hope this problem was useful to all of you. Please do practice this and make sure that you're not plugging in the wrong numbers and so on. It is very easy to make a mistake in these problems. Okay, they're simple geometric problems, but it is fairly straightforward to make calculate these things, but also easy to make mistakes on them. Okay, so please practice and stay safe. Bye bye.